Dear students, I hope you have listened my previous lectures on YouTube, and also I hope you gone through the notes which I provided along with YouTube classes. Okay, so today I want to explain you about stereoheterotopic ligands and phases. In the last class I tried to explain you some basic terminology like homomorphic units, the definition and the classification of homomorphic units. Okay, as I already explained you and inform you that homomorphic units can be broadly classified as homotopic units and heterotopic units. Homotopic units further divided into homotopic ligands and homotopic phases, right? Similarly, heterotopic units can be further divided as stereoheterotopic units and structurally heterotopic units. Stereoheterotopic units further divided as enantiotopic units and diastereotopic units. So as I tell you in my previous classes, ligands may be considered as atoms or groups, and phases are different. So atoms, groups and phases, all of them together can be considered as unit, right? Again, enantiotopic enantiotopic ligands further classified as units, ligands and phases. Similarly, diastereotopic units can be diastereotopic ligands and diastereotopic phases. Okay. Finally, structural heterotopic units, and those units can be classified as structural heterotopic ligands and structural heterotopic phases, like that. Okay. So today I am going to explain you stereoheterotopic ligands and phases. Okay. First, let me define you what is stereoheterotopic atoms or groups or ligands and phases. Okay. All right. The atoms are groups. The atoms are group are phases when substituted or by addition with new atom or group liberates stereoisomers. What are stereoisomers? They may be enantiomers or diastereomers. Okay, are known as stereoheterotopic ligands. Okay, so that is the definition of stereoheterotopic ligands. The atoms, groups, phases when substituted or by addition with new atom or group liberate stereoisomers. Okay, stereoisomers, they may be enantiomers and diastereomers, are known as stereoheterotopic ligands. Stereoheterotopic ligands and phases are either enantiotopic or diastereotopic depending upon the products formed, whether enantiomer or diastereomer respectively. Okay, so enantiomers, stereoheterotopic ligands depends upon the formation of products in that particular reaction. If enantiomers formed in that reaction, then those atoms or groups can be considered as enantiotopic ligands. If in that reaction diastereomers formed, then those atoms or groups can be considered as diastereotopic ligands. Okay, so this is the simple definition you need to understand. Okay, the first let us try to learn about enantiotopic ligands and enantiotopic ligands. The stereoheterotopic ligands can be classified as enantiotopic ligands and phases. The second one is diastereotopic ligands or phases. How they can be decided? Based on the formation of the product in that particular reaction. Okay, if in that reaction enantiomers formed, then they can be considered as enantiotopic ligands and phases. If in that reaction diastereomers are formed, then they can be considered as diastereotopic ligands or phases. Okay, so depending upon the formation of the product, whether enantiomers or diastereomers respectively, so they can be classified like that. First, let us try to understand about enantiotopic ligands and phases. Okay, first let us see about enantiotopic ligands or phases. So what is enantiotopic ligands? What is enantiotopic ligands? The ligands in a molecule are exchangeable with secondary kind of symmetry elements like center of symmetry, plane of symmetry, alternative axis of symmetry. Okay, are said to be enantiotopic ligands. Okay, the ligands in a molecule are exchangeable or interconvertible by secondary kind of symmetry elements Ci or sigma or Sm. What is Ci? Center of inversion or center of symmetry. What about sigma? In symmetry elements, it is plane of symmetry. And what about Sn? It indicates alternative axis of symmetry. So these three kinds of symmetry elements, if produces the ligands, whether exchangeable, then they can be considered as enantiotopic ligands. Okay, the ligands in a molecule are exchangeable by secondary kind of symmetry elements like center of symmetry, plane of symmetry, alternative axis of symmetry, are said to be enantiotopic ligands. Okay, that is the definition for enantiotopic ligands. I'll give you examples so that you can understand easily about enantiotopic ligands. Okay, so do you remember what is the definition for homotopic ligands? In homotopic ligand, so there is a Cn axis of symmetry. Okay, the ligands in a molecule exchangeable or interconvertible by Cn axis of symmetry and produces homomers can be considered as homotopic ligands. That was the definition for homotopic ligands. Okay, so the difference between homotopic ligands and enantiotopic ligands: in homotopic ligands, the symmetry element is Cn axis of symmetry. Okay, Cn axis of symmetry. Okay, but in this case, secondary kind of symmetry elements works out. Okay, what are those? Center of symmetry, plane of symmetry, alternative axis of symmetry. If these kind of symmetry elements, with the help of these symmetry kind of elements, if the ligands are exchangeable or interconvertible, then they can be considered as enantiotopic ligands. Okay, so I'll give you the example for that. Suppose, so this is one of the example. I can write as CH2, CH3, CH2OH. So this is the simple ethanol, right? Simple ethanol molecule. This can be write as the central carbon. One is hydroxyl group, the another one is CH3 group, and two hydrogens are there, HA, HB. Okay, this structure can be, so just you check, is there any CN symmetry element in this? No, because these two atoms or groups which are attached are different. So there is no CN axis of symmetry in this molecule. But what is there? Okay, but what is there? So we can write that molecule for your understanding like this: COH, CH3, HA and HB. So is there any secondary kind of symmetry element in this molecule? Yes. So if you have a plane in this like this, so this is the plane of symmetry. Okay, so if you bisect this molecule with this axis, okay, so you will get two equal offs. Two equal offs you will get. So that means this molecule has plane of symmetry. Plane of symmetry. Okay, it divides, this plane divides two equal parts of that molecule. Therefore, it has plane of symmetry. So as I given definition previously, that if any groups or the atoms here, HA and HB, HA and HB, these two atoms or groups, okay, exchangeable or interconvertible by the help of secondary kind of symmetry element like plane of symmetry. Therefore, these two atoms can be considered as enantiotopic ligands. Enantiotopic ligands. Enantiotopic ligands. Okay, so I hope now you understand what is enantiotopic ligands. Okay, as I said, as I defined this enantiotopic ligands, the atoms or the ligands, ligands means atoms or groups. Okay, the ligands which are exchangeable or interconvertible by the help of secondary kind of symmetry elements like plane of symmetry are known as enantiotopic ligands. Therefore, HA and HB, these two ligands can be considered as enantiotopic ligands. I'll give some more examples to understand clearly about the definition and concept of enantiotopic ligands. Okay. The other one, suppose, let me please check yourself with this example. CH Cl2 CH Cl2 CH2 Cl2, right? Methylene dichloride. Okay, CH2Cl2. So this can be, we can write like this Cl Cl and one hydrogen Ha, and you can write another hydrogen Hb. So in this molecule, so if you, with this axis, if you rotate this one, you will get about 180 degrees, you will get same, these two are exchangeable. These two ligands and these two ligands are exchangeable and interconvertible with the Cn axis of symmetry. That means C2 axis, here about 180 degrees rotation. So that means, as I said in the definition, these Ha and Hb, Ha and Hb and these two Cls belongs to homotopic ligands. Homotopic ligands, because of Cn axis of symmetry, C2 axis of symmetry. With the C2 axis of symmetry, those ligands or atoms or groups are exchangeable, are interchangeable, are interconvertible. Therefore, they can be considered as homotopic ligands. So here, whenever the Cn axis of symmetry, with the help of Cn axis of symmetry, the ligands in a molecule are exchangeable or interconvertible, they can be considered as homotopic ligands. If the different symmetry kind of elements like center of symmetry, plane of symmetry, alternative axis of symmetry, with the help of those symmetry elements, if ligands are exchangeable or interconvertible, they can be considered as enantiotopic ligands. Okay, so that is the slight difference between homotopic ligands and heterotopic ligands. Okay, in homotopic ligand, Cn axis of symmetry, place Cn axis of symmetry, Cn axis of symmetry plays important role. In heterotopic units, in heterotopic ligands, so what are those? Ci, center of inversion or center of symmetry, sigma, that means plane of symmetry, and Sn, that means alternative axis of symmetry. Okay, so if symmetry element with the help of Cn axis of symmetry, then homotopic. If these secondary kind of symmetry elements, they can be considered as heterotopic or enantiotopic ligands. Okay. So these are homotopic ligands, and first example are heterotopic ligands. I'll give you one more example. Okay. CH2 ClBr. So this is the molecule. Okay, this can be written as C, chlorine and bromine, and Ha and Hb. Okay, is there any symmetry, Cn axis of symmetry in this molecule? That means no, because there are two different groups. Okay, so this molecule can be represented for your convenience like this: C, Cl and Br, Ha and Hb. So if you bisect a plane like this, in the middle, this is the sigma, plane of symmetry. if you bisect this molecule with this plane, you will get equal two parts of that molecule. So that means in this molecule there is a plane of symmetry. So whenever plane of symmetry is exist, with the help of plane of symmetry, the ligands are exchangeable, are interconvertible. They can be considered as enantiotopic ligands. So with this plane of symmetry, these two ligands or atoms HA and HB are exchangeable, are interconvertible. Therefore HA and HB are enantiotopic ligands. Enantiotopic ligands, that means atoms are groups. Okay, so this is another example to understand about enantiotopic ligands. I'll give you some more examples to understand very clearly about enantiotopic ligands. Propionic acid, I'll give you this example also, CH2COOH. So this is the propionic acid. So you can write this center carbon here and one COOH attached and one CH3 attached and two hydrogens, HA and HB. Okay, so is there any CN axis of symmetry in this molecule? If you look at, no, not possible. But for your convenience, you can write like this: COOH and CH3, HA and HB. So here, if you bisect this molecule with this plane, okay, this is plane, that plane equally divides or equally separates two parts of this molecule. Okay, that means this molecule has plane of symmetry. Therefore these two atoms or ligands can be considered as enantiotopic ligands. HA and HB can be considered as enantiotopic ligands, ETL, enantiotopic ligands, because of plane of symmetry in this molecule, which divides two equal parts of that molecule. So therefore these two atoms or groups or ligands exchangeable with each other are identical. Therefore these two HA and HB, or these two hydrogens, or these two ligands, can be called as enantiotopic ligands. Okay, so that is I hope with these examples it is easy for you to understand about enantiotopic ligands. Okay, enantiotopic ligands. I'll give you some more examples. Suppose this is the dibromo substituted molecule, CH2CHOH, COOH. Suppose this is one of the example. How can we identify or distinguish whether they are homotopic or heterotopic ligands? Because these two bromo atoms or groups are ligands to which they belongs to. Are they belong to homotopic or they belong to heterotopic? Let us find out. Okay, suppose you can write this one as COOH and CH2OH and bromine and another bromine. So you have plane of symmetry in this plane. Okay, so this is plane of symmetry. With this plane of symmetry, this molecule can be divided into two equal parts. Therefore it has plane of symmetry. these two bromine atoms or groups, these two bromine atoms or groups or ligands can be called as enantiotopic ligands. Enantiotopic ligands. Okay, so this is another example you need to understand and you need to practice to learn about enantiotopic ligands. So I will give one cyclic compound example. pH, pH, and I also give you another example, just slight difference, with this slight difference, pH, 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 or you can write just hydrogen, okay, hydrogen HA or hydrogen HB. So this is also HA, this is also HB. What is the difference between these two isomers? The only difference is the the stereochemistry is different. Okay, so in this first example, both these ligands or atoms are in the same plane, but in this case they are in different plane. Okay, so first let us take this molecule, and is there a plane of symmetry in this? Is there any plane of symmetry in this? No. No, sorry, no center of symmetry. CN axis of symmetry. If you have CN axis, if you rotate, okay, this upside will go down and this will go down, that one. Okay, so therefore no CN axis of symmetry, but only plane of symmetry is there. If you bisect this molecule with this plane, you will get two equal parts. You will get two equal parts. So plane of symmetry present in this case. But here, what is the therefore HA and HB are enantiotopic ligands. Enantiotopic ligands. What about this example? So is there any plane of symmetry in this molecule? No, because one hydrogen attached away from the viewer, this hydrogen attached towards the viewer. So if you bisect from the middle, you will not get equal parts of this molecule. So therefore there is no plane of symmetry. But what is there? So there is a CN axis of symmetry in this molecule. Okay, if you rotate through this axis about 180 degrees, that means C2 axis. Okay, so this hydrogen, if you rotate, will go away. This hydrogen will come up when you rotate 180 degrees. So that means in this example, in this isomer, there is CN axis of symmetry, C2 axis. So therefore HA and HB are homotopic, not heterotopic, homotopic, because of C2 axis of symmetry. But in this case, there is a absent of CN axis of symmetry, but plane of symmetry is present in this molecule. So therefore, with this plane, you will these two atoms or ligands are exchangeable, or they are equal, they are interconvertible. So they will produce enantiomers or diastereomers when you do some reactions. Therefore, HA and HB are enantiotopic ligands. Enantiotopic ligands. You understand? So here it is homotopic, here it is heterotopic, enantiotopic ligands. So one more example or two more examples I'll give you on enantiotopic ligands. Okay, suppose, so this is the molecule HA, HB, BR, BR. Okay, so have you find out, are you able to find out these two bromines are homotopic or heterotopic? So here is the first you find out, first you look at, is there any CN axis of symmetry in that molecule? So these two are in one plane, therefore there is no CN axis of symmetry in this example. But what is there? There is a plane of symmetry. But there is a plane of symmetry. If you divide these two with this plane, you will get two equal parts through the plane. Therefore, these two bromines can be considered as enantiotopic ligands. They can be considered as enantiotopic ligands because of plane of symmetry. With the help of plane of symmetry, these two bromines are exchangeable, interconvertible, and they can produce enantiomers or diastereomers when substitution takes place. So therefore, these two bromines can be considered as enantiotopic ligands. I'll give another example. So till now you have seen plane of symmetry. With the help of plane of symmetry, the two atoms or groups or ligands can be exchangeable. Then they can be considered as enantiotopic ligands. So now I'll give you different example which has a different symmetry element in that. Okay, like COOH, tartaric acid. I'll write Saha's formula for that. Okay, COOH, COOH, OH, OH, hydrogens and hydrogen. So if you want to identify the center of symmetry, you can connect the two groups which are same in the molecule. Okay, so if you connect two groups which are same in that molecule, so if it has center, then it can be considered as center of symmetry. Say for example, here you can connect this OH and this OH. These two groups are same. You can connect like this, and these two hydrogens are same. Okay, and these two COOH groups are same. So while you connecting the same groups with a line, if those lines bisect at one center, here one center formed. Okay, so this is called center of symmetry. Center of symmetry. Okay, center of symmetry. What is center of symmetry? When you connect the same groups in that molecule, if all lines go through one center, then that center is called center of symmetry. So here it has center of symmetry. So as I said in the beginning about definition, did you remember? Okay, the ligands in a molecule, the ligands in a molecule with the help of exchangeable or interconvertible by secondary kind of symmetry elements like center of symmetry, plane of symmetry, alternate axis of symmetry. Okay, so those atoms or groups or those ligands can be considered as enantiotopic ligands. So here there is a center of symmetry, so therefore these COOH groups and so here all the COH groups and hydroxyl groups and hydrogens. Suppose I'll label as HA and HB. So HA and HB are enantiotopic ligands. Enantiotopic ligands. Enantiotopic ligands. Okay. So because of center of symmetry present in this molecule. With the center of symmetry, these two hydrogens are exchangeable or interconvertible, will produce enantiomers when substitution additions takes place. Therefore, HA and HB are enantiotopic ligands. Enantiotopic ligands. Of course, we will substitute or will react to these hydrogens. Therefore, I wrote only HA and HB. Okay, but all these groups are enantiotopic ligands because they have center of symmetry in that molecule. Okay, so this is about enantiotopic ligands. Okay, so finally I'll give you one more example. It's a cyclohexanone HA HB, and also I'll give so here is there any center of symmetry or any plane of symmetry exist in this molecule? Okay, yes. So if you have a plane like this, okay, with this, okay, if you bisect this molecule from top, you will get two equal parts. Okay, two equal parts. So therefore HA and HB are enantiotopic ligands. Enantiotopic ligands. Enantiotopic ligands. Because plane of symmetry, if you bisect this molecule through this plane, one hydrogen is away from the viewer, this hydrogen is towards the viewer. Okay, so therefore this molecule can be bisected two equal parts with that plane. So therefore plane of symmetry exists in this molecule. Therefore these HA and HB, two atoms or groups or ligands, are called enantiotopic ligands. Okay, so I hope you have seen more number of examples to understand about enantiotopic ligands and phases. So this is symmetric criteria. Okay, symmetric criteria. By using symmetric criteria, you can identify whether they are homotopic or heterotopic ligands. Okay, so in homotopic ligands also we have done the same thing by using symmetric criteria, and the second method is substitution or addition method or substitution criteria. Also by using that criteria we can identify whether the given molecule has have homotopic ligands or heterotopic ligands, that we can identify. Okay, so let us see about the second criteria. B criteria is substitution criteria. Substitution criteria or substitution method. Okay, substitution method. The atoms first, according to this criteria, we can define enantiotopic ligands. Okay, the atoms are groups. The atoms are groups. The atoms are groups in a molecule. When substitution or by addition generates with a new atom or group, generates or provides enantiomers are said to be enantiotopic ligands. So this is the definition according to substitution criteria. According to symmetric criteria, you defined as the ligands in a molecule which are exchangeable or interchangeable with the help of secondary kind of symmetry elements like center of symmetry, plane of symmetry and alternative axis of symmetry are said to be enantiotopic ligands. Okay, so that is according to symmetric criteria. According to substitution criteria, we can define enantiotopic ligands like this. The atoms groups in a molecule when substitution or by addition with a new atom or group generates enantiomers are said to be enantiotopic ligands. Okay, so I'll give you examples. So that you can understand very well about substitution criteria. Okay, so Cl and Br, Ha and Hb. So hypothetically you can substitute with some Ha, hypothetically substituted with fluorine, then what you get? The product is Cl, Br, Hb and F. So if you substitute another with fluorine, another side of ligand or atom, you will get Ha and F. These two are enantiomers. Okay, these two are enantiomers. Therefore, these two Ha and Hb are enantiotopic ligands. Okay, so can I define once again about these enantiotopic ligands based on substitution criteria? The atoms, these two atoms, okay, these two hydrogen atoms are groups, are ligands in a molecule when hypothetically substituted with or addition with a new atom or group. Here, what is the new atom? We are taking fluorine. Okay, so we have substituted these hydrogens with chlorine. Okay, and when they generate enantiomers, so in this reaction the two enantiomers are formed. So here these two atoms or groups on hypothetical substitution produces enantiomers. Therefore, these two atoms or groups or ligands can be considered as Enantiotopic Ligands. Okay, Enantiotopic Ligands. So this is the substitution criteria by which you can identify Enantiotopic Ligands. Okay, I'll give some more examples. Suppose this is the HA and HB. So these two atoms or groups, are they enantiotopic or homotopic? How to find out? By substitution criteria. You can substitute these two, hypothetically substituted HA with hydroxyl group, you will get this compound HB and OH, COH and CH3. The other one possible, if you substitute HB with hydroxyl group, so you will get COOH, OH and HA and CH3. What are these two? They are non-superimposable mirror images. That means they are enantiomers. Okay, so these two atoms or groups or ligands on hypothetical substitution with hydroxyl group, a new group, hydroxyl group, produces or generates enantiomers. Therefore, these HA and HB can be considered as enantiotopic ligands. Can be considered as enantiotopic ligands. Okay. Enantiotopic ligands. Okay. So I'll give one more example. HA, HB, HA and HB. If you substitute HA with hydroxyl group, you will get OH. If you substitute HB with hydroxyl group, you will get both are stereoisomers. Okay, both are stereoisomers. Okay, so if you assign the absolute configuration of this, first priority, second priority, third priority. So this is anti-clockwise. Anti-clockwise, yes, R configuration, because hydrogen is towards center. So what about this? This is S configuration. So that means RS means they are enantiomers. Okay. So these two atoms or groups or ligands, when hypothetically substituted with a new atoms or groups, if they produces enantiomers, they can be considered as enantiotopic ligands. They can be considered as enantiotopic ligands. Okay. So this is about substitution criteria. Okay. So this is about substitution criteria. Okay. So by two methods you can find out or you can distinguish whether they are enantiotopic ligands or homotopic ligands. Okay, symmetry criteria and substitution criteria. Okay, so they can be worked out on matter. Okay, so you need to understand about enantiotopic phases. Okay, enantiotopic phases. Now ligands, you have learned about ligands and enantiotopic phases. Enantiotopic phases. The addition of atoms or groups, the definition for that, the addition of atoms or groups, the addition of atom or groups to either the phases of molecule leads to enantiomers, then those phases can be enantiotopic phases. Those phases can be enantiotopic phases. Okay. So the addition of atom or group to either the phases of a molecule leads to enantiomers. Those phases can be considered or called as enantiotopic phases. I'll give examples so that you can understand. So what about these? Suppose formaldehyde. So it has two phases. From left one is one phase, from right side the another phase. This is the phase 1 and this is the phase 2. Okay. Suppose acetone molecule, this is phase 1 and phase 2. Okay. So I'll give one more example, pH and CH3, F1 and F2. In these three examples, suppose in this example, so either the phases, okay, you can add the new atom or group from phase towards the phase 1 or from the phase 2. You will get the same product. You will get homomers. Therefore, this F1 and F2 are homotopic phases. So what about this example? In this example also homotopic phases, because the two groups or atoms are same in this molecule. What about this? This example is different. Okay. So if a new atom or group added through this way or through this way, you will get the different isomers. They are nothing but enantiomers. Therefore, these two F1 and F2 can be considered as F1, F2. Two phases can be considered as enantiotopic phases. Okay, because if the new atom or group added towards phase 1, that will give one isomer. If that atom or group added towards the another phase, that will give another isomer. So this molecule can produce enantiomers by addition of atom or group to either phases of a molecule leads to enantiomers. Therefore, these two phases F1 and F2, this is one phase and this is the another phase, can be considered as enantiotopic phases. Okay. Enantiotopic phases. I'll give one more example. This is F1 and this is F2. Both the phases are different. They can produce enantiomers. Therefore, F1 and F2 can be considered as enantiotopic phases. They can be considered as enantiotopic phases, because if the reagent, newly added reagent from this side, they will form one isomer. If they comes from this way, that will produce another isomer. So therefore this F1 and F2 can produce enantiomers. Therefore the F1 and F2 phases can be considered as enantiotopic phases. Okay, they can be considered as enantiotopic phases. So I hope you understand about enantiotopic ligands and phases. The another method, B method, substitution or addition method. Addition method to find out whether they are enantiotopic phase or homotopic phase. Okay, suppose this CH3H. Suppose if you react this molecule with hydrogen cyanide, okay, it can come from this side or it can come from this side. Two phases are there. Okay, so this can be F1 and this can be F2. Okay, suppose if it is from F1 substituted with Cn, you will get CH3 hydrogen and Cn hydroxyl group. Suppose the reagent attacked from F2 phase, through F2 phase, you will get this molecule CH3. OH Cn. So both the products, both the isomers are enantiomers. Okay, both the isomers can be considered as enantiomers. They are non-superimposable mirror images. So therefore, according to substitution or addition method, we can find out these two phases, F1 and F2. These two phases can be considered as enantiotopic phases. So F1 and F2 can be enantiotopic phases. You understand? Okay. So this is about substitution or addition criteria. The second criteria by which you can understand about enantiotopic ligands. Okay, all these examples are I hope with these examples you understand about enantiotopic ligands. Okay, stereoheterotopic units. In stereoheterotopic units, you can divide them as stereo enantiotopic units and stereo diastereotopic units. In stereo enantiotopic units, you have seen about stereo enantiotopic ligands and stereo enantiotopic phases. Now we'll see about diastereotopic ligands. Diastereotopic ligands. Diastereotopic ligands. Okay. So what is diastereotopic ligands? The atoms are groups. The atoms are groups which are not interchangeable, or exchangeable by any symmetry element. Are said to be Diastereotopic ligands. Diastereotopic ligands, DSL. Okay, the atoms or groups which are not exchangeable or interchangeable by any symmetry elements are said to be diastereotopic ligands. Suppose if a chiral center directly attached to atom which having two identical subunits produces diastereomers are called diastereotopic ligands. I will give examples so that you can understand about diastereotopic ligands. Okay, suppose, so this is the molecule example B, C, HA and HB. So this is the chiral center. Okay, in this molecule there is no any symmetry element. Okay, no plane of symmetry, no center of symmetry, no alternative axis of symmetry, no CN axis of symmetry. Okay, but suppose this chiral center, okay, this is chiral center, directly attached to the atom which having two subunits HA and HB, which have same subunits, identical subunits. Okay, these two identical subunits. Okay, if a chiral center directly attached to an atom which having two identical subunits, that subunits can be considered as diastereotopic ligands. You got my point, the definition? Okay, so the ligands, the atoms or groups which are not exchangeable or interconvertible by any symmetry element, they can be considered as diastereotopic ligands. Otherwise, if a chiral center, this chiral center directly attached to an atom which having two subunits, same identical subunits, then these two subunits can be called as diastereotopic ligands. That means in this HA and HB are diastereotopic ligands, atoms or groups. Okay, this HA and HB. Okay, so these two can produce diastereomers when substitution reactions or addition reactions. So this is about diastereotopic ligands. Best example is this acid hydroxyl group and hydrogen, HA and HB is COH. Okay, so in this molecule, this HA and this HB, they can be considered as diastereotopic ligands. They can be considered as diastereotopic ligands because in this molecule there is no symmetry at all. Okay, that is one thing. And the other thing, this chiral center directly attached to the atom which having two identical subunits. Therefore, these two subunits or atoms or groups can be considered as diastereotopic ligands. Okay, so finally I'll put substitution criteria, the second one, substitution criteria. Okay, substitution criteria, suppose I'll give some example by which you can understand. X, HA, HB, okay. Suppose HA substituted with chlorine, you will get C double bond C, Cl, X, H and HB. And the other one, HB, if you substituted with that one, HA, X, H, and this one Cl. This is cis and this is trans. Two isomers will be formed. Those are diastereomers. Okay. So therefore, this HA and HB can be considered as Diastereotopic Ligands. HA and HB can be considered as Diastereotopic Ligands. So this is the substitution criteria by which you can identify or you can distinguish whether they are Diastereotopic Ligands or not. You can easily understand. So finally, I'll give you Diastereotopic Faces. Structural. The final one is structural heterotopic units. Units may be ligands or phases. Okay, structural heterotopic units. Suppose we'll see CH2, this H1 and this is H2. Okay, so this is the propane molecule. If you substitute H1 with chlorine, you will get CH3 CH3 Cl, here Cl. Okay, if you substitute H2 with chlorine, you will get CH3 CH2 CH2Cl. These two are structural isomers. Okay, the positional isomers. Here it is in the case of first one, it is 2-chloropropane. It is so 3-chloropropane. So they have same molecular formula, same connectivity, but the position is different. They can be considered as structural isomers. Okay, so this H1 and H2B can be considered as H1 and H2 can be considered as structural heterotopic units, heterotopic ligands. So one more best example. Suppose so you have OH, H1, H2, H3. These three H1, H2, H3 are structural heterotopic units, because if you substitute this H1 and H2, H3 with hydroxyl group or chlorine group, you will get ortho, meta, para compounds, or they can be structural isomers. Therefore, these two H1, H2, H3, these three atoms or groups or ligands can be considered as structural heterotopic ligands. Okay, so I want to close this class at this moment. So in the next class I will continue the another topic. Thank you. Bye.